Okay, 12, 13, so 11. Okay, so again, given vectors, let's say A1, A2, all the way up to AK. So each of these has a little vector symbol over top. We want to make sure that when we're writing vectors, we indicate that with vector symbols. And each of these vectors, say a vector in Rn. So that means each one of these vectors has n entries. So like A1 will have a first entry and a second entry and a third entry, and there'll be n of them all together. So there are n entries altogether. And so we can think of it as an arrow in Rn. So given vectors, k vectors in Rn, and given another vector, well, let me start with this first. So if we have some scalars, which I'll call x1 through xn, x1, x2, all the way up to, sorry, xk are scalars. So just numbers. Then x1 times a1 plus x2 times a2 plus all the way up to xk times ak is called a linear combination. Of vectors a1 through ak. That thing's called a linear combination. So for example, linear combination, that's what I'm defining here. So for example, if I give you, say, two vectors in R3, let's say A1 is the vector 1, 2, 3, and let's say A2 is the vector 1, 1, 1. And let's let x1 be blah 2, and x2 equals -1. Then here's a linear combination of these two vectors. So I can just take x1 times a1 plus x2 times a2, and so that is equal to 2 times the vector 1, 2, 3 plus -1 times the vector 1, 1, 1. And that's, so 2 times 1, 2, 3 is 2, 4, 6. And -1 times 1, 1, 1 is -1, -1, -1, -1. -1, -1, -1. And if I add those up, 2 plus -1 is 1, 4 plus -1 is 3, 6 plus -1 is 5. That's a linear combination of these two vectors. I could have picked any two numbers. I just picked 2 and -1 out of the air. And so the vector 1, 3, 5 is expressed as a linear combination of these two vectors. One, 3, 5 has been expressed as a linear combination of A1 and A2. So A1, let's just sketch a picture here. So A1 is the vector 1, 2, 3. So coming out 1 on the x-axis, 2 on the y-axis, and going up 3. So over 1, 2, up 3. So here's vector A1. And vector A2 is 1, 1, 1. Out 1 on the x-axis, over 1 on the y-axis, up 1 on the z-axis. There's vector A2. Sorry, my picture is so smushed there. It's just because A2 is sort of coming out in this direction, it looks short. And the vector 1, 3, 5 has been expressed, if I take one of these, sorry, 2 of these, minus 1 of those, I get the vector 1, 3, 5. Now we talked last time, if I take all the vectors I can express as linear combinations of those two vectors, where are all those vectors? So if I take, one of these plus one of these, that gives me a vector. If I take one of these minus one of these, that gives me a vector. If I take 2 of these minus 3 of these, I get a vector. If I take all the vectors, so 1, 3, 5 is one of them. If I take all the vectors that can be expressed as a linear combination of those two vectors, where do they all lie? On a what?
On a plane.
Yeah, exactly. They're all on a plane. They're on the plane which goes through these two vectors. So the set of all linear combinations of A1 and A2 are on a plane, are on the plane that goes through the origin and those two vectors. And we call that the span. So this plane is called the span. In this case, it's a plane. So the set, let me just rewrite the definition over here. Set all vectors you can get as a linear combination of, let's say, A1 through AK. And we're careful to write vector symbols over vectors. If I ever forget to do that on the blackboard, then remind me. Is called the span of A1 AK. And you can write it like this. Span, open curly braces, A1, A2, up to AK. Now, well, let me just look at your pictures. You're still writing. Tell me you're still writing. So Jalen, you correctly answered that the span of these two vectors would be a plane because you noticed that the two vectors that I gave you, the vectors, whatever they were, 1, 2, 3, and 1, 1, 1, were not parallel. They're not parallel. They're pointing in different directions. If one was parallel to the other, you'd be able to spot that immediately because one would just be a multiple of the other. Like a vector parallel to 1, 2, 3 could be like -2, -4, -6, where I get from this to this just by multiplying by -2. It's easy to spot when two vectors are parallel. So you spotted that they weren't parallel. And so the span of two vectors that aren't parallel is the plane which goes through those two vectors. If two vectors are parallel and I take the span, what shape is the span going to have? If the two vectors are parallel?
A line?
Yeah, it's just going to be a line, right. If I have 10 vectors and they're all parallel, the span is just going to be a line. The span of those 10 vectors is just going to be a line. Because you can't get off that. I mean, the only direction you can move is in the direction of those vectors, and if they're all parallel, if they're all parallel, you can't get off that line. Okay. So if A1, A2, up to AK, and the vector B are all vectors, say in Rn, R1 is just the real line, R2 is the XY plane, the X1, X2 plane, R3 is going to be three-dimensional space, R4 is four-dimensional space, whatever that means, however you visualize that or don't. You don't have to. R5, five-dimensional space, and so on. So these vectors are all vectors in the same dimension. They all have the same number of entries. So say if n was equal to 8, each one of these vectors would have 8 entries. A first one, a second one, a third one, a fourth one, all the way up to the 8th one. If we're in R2, each one has 2 entries. If we're in R3, each one has 3 entries, and so on. So if these are all vectors in the same, that have the same number of entries, and x1, x2, all the way up to xk are numbers, let me say are real variables. So then x1 times a1 plus x2 times a2 plus x3 times a3. Notice I'm putting vector symbols over top of all my vectors, but not over any of my scalars, plus all the way up to xk times ak equals b is called a vector equation. Called a vector equation. So for example, let's say n equals 3, so we're working in R3. And let's say A1, I'm going to pick exactly the same example I had before, is 1, 2, 3. And let's say A2 is equal to, A2 is equal to 1, 1, 1. And let's say B is 1, 3, 5. So if you look back to what you were writing about 5 minutes ago, I had the vectors 1, 2, 3, 1, 1, 1, and 1, 3, 5. Then this is a vector equation. Solving that, solving that vector equation means finding the values of x1 and x2 that make that true. Solving that vector equation means finding values x1 and x2 that make that equation true. If I had more vectors on the left-hand side, I'd need more variables. Let's go ahead and massage this into a different form. You know how to take a vector and multiply by a scalar. You just take the scalar and multiply every single entry in the vector by the scalar. So I can rewrite this. If I take x1 and multiply it by 1, 2, 3, that's just x1 times 1, x1 times 2, 2x1, x1 times 3, 3x1. If I take x2 and multiply it by 1, 1, 1, That's just x1, sorry, x2, x2, x2. All I did is multiply the x1 into 1, 2, 3, and the x2 into 1, 1, 1. That's all you do when you multiply a scalar by a vector. You multiply the scalar by every single entry in the vector. And that's supposed to equal 1, 3, 5. We also know how to add two vectors. When you add two vectors, you just add the components. So the left-hand side here is x1 plus x2. What we have here is 2x1 plus x2. What we have here is 3x1 plus x2. And it's supposed to equal 1, 3, 5. And we know what it means for two vectors to be equal. Two vectors are equal if their first components are equal and their second components are equal. In this case, their third components are equal. If they had a fourth component, they'd have to be equal. So this is the same as writing x1 plus x2 is equal to 1. 2x1 plus x2 is equal to 3. And this is the same as saying 3x1 plus x2 is equal to 5. So this vector equation can also be written as this system of linear equations. We already know that this system of linear equations, so this and this, are equivalent. We already know that this is equivalent to an augmented matrix. The augmented matrix is 1, 1, vertical line, 1, 2, 1, vertical line, 3, 3, 1, vertical line, 5. We already know how to solve augmented matrices. Of course, we already know how to solve that. We know we can solve it in terms of augmented matrices. So we just have three different forms of the same thing now. So every vector equation is equivalent to a system of linear equations and equivalent to an augmented matrix. And you should easily be able to go back and forth. If I gave you this and I said write it as a vector equation, you should just be able to say, oh, okay, well, x1 times the vector 1, 2, 3, there it is, 1, 2, 3, plus x2 times the vector 1, 1, 1 equals the vector 1, 3, 5. You should be able to take that and write that as easily as you can take this and write that. You should be able to go back and forth between these three easily. There's really nothing to it. It's just a notation change. Is everybody okay with that? When we're actually doing computations, this is the form that we're going to keep things in most often because that's the easiest form to do computations in. By the way, just looking back at your notes, without even doing it, because we basically came up with the 1, 3, 5 in the first place, what is the solution to this equation? What is x1 and what is x2? Just looking back at your notes. Because where did we come up with the 1, 3, 5 in the first place?
Oh, there were 2 and minus 1?
Yeah, it was 2 and minus 1. x1 was 2 and x2 is minus 1. So the solution to this vector equation is x1 equals 2, x2 equals minus 1. That's how we came up with 1, 3, 5 in the first place. We expressed 1, 3, 5 as a linear combination of these two vectors, 1, 2, 3, and minus 1, minus 1, minus 1, using x1 equals 2 and x2 equals minus 1. Is everybody okay with this so far? I think that's it for that section. I think I've mentioned everything I want to say. Yep. Okay, let's move on to section 1.4. Does everybody have everything copied down? Can I erase what's on the blackboard? I'd like to get a fresh start. Tyler, are you good? Awesome. Everybody else? Some of you I can't see. Oh, thumbs up. Thank you. Got him. All right, awesome. So I want to start out by multiplying a matrix times a vector. So given an n by m matrix, so n is the number of rows, and m is the number of columns. Does your book use n by, they use m by n. I'll use m by n too. M by n. So this is the number of rows, and this is the number of columns. And a vector, oh, I guess I should give this matrix a name. I'll call it A. So given an m by n matrix A and a vector x in Rn, so this vector has the same number of entries that this matrix has columns. So let's let A be the matrix. I'll call its first entry, the upper left-hand corner, I'll call A sub 1, 1. I'll call the entry immediately below it A sub 2, 1. All the way down to, we said this thing has m rows, so this will be A m1. So right next to this, I'll have A 1, 2, first row, second column, and right below that, I'll have A 2, 2, all the way down to A m2. And I'll continue all the way over to my last column. Since I have exactly n columns, this will be A1n, A2n, all the way down to AMN. Write it like that. But I'm also going to write it like this, as a sort of a shorthand notation. That's a lot of letters to write. I'm going to group it by columns. I'm going to say A1 is this whole column. It's this whole column vector. So I will think of A1 as the, so here's vector A1, my first column. And vector A2 will be the second column. Oh, my voice is cracking today. A2 with a vector symbol over top. So each one of these vectors has exactly n entries, all the way up to A, so dot, 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 up to A n, my last column. So this is still an m by n matrix. It's just that I'm writing each column as a single letter. So here's A m. Sorry, that's an m. No, it's an n. It's an n. So A1 and A2 up to AN. These are all vectors with M entries in it. Each one has M entries. There's A1, there's A2, all the way up to AN. But X has a different size. X has N entries. So X1, X2, all the way up to Xn. So each of these has M entries, but X has N entries. X has the same number of entries as this matrix has columns. That's important. Then A times X is defined like this. A times X is equal to X1 times the first column plus X2 times the second column plus X3 times the third column, all the way up to Xn times the nth column, which is why it's important for X to have the same number of entries as the matrix has columns. So let's do an example. Let's say my matrix A, I will give you a matrix, how about 1, 2, 3, 4, 5, 6. So this is a 2 by 3 matrix. Two rows, 3 columns. And now if I give you a vector and I'm going to multiply A by X, that vector is going to have 3 entries because it has to have the same number of entries as this has columns. So how about 1, -1, 2. Then A times X, which is just 1, 2, 3, 4, 5, 6 times 1, -1, 2. Is equal to this number times the first column, so 1 times 1, 4, plus this number times the second column, plus this number times the third column. And we can just go ahead and do this algebra now. So 1 times 1, 4 is 1, 4. -1 times 2, 5 is -2, -5. And 2 times 3, 6 is 6, 12. And when we add these up, we just add up their components. So 1 minus 2 plus 6 4 minus 5 plus 12. I'm getting 5, 11. So when you take a matrix and you multiply it by a vector, you're just taking this entry times the first column, this entry times the second column, this entry times the third column, and adding them all up. So you can see that what you get has a different size than the vector. What you get is going to have the same number of entries as your matrix had rows. Whereas the original vector over here had the same number of entries that the matrix had columns. And if the matrix isn't square, those two numbers are different. Is that good? All good? Okay. Now, this is not, if I'm actually asked to do this multiplication, I don't write this out. This is not how I do this. Let me show you how I multiply a matrix times a vector when I'm actually doing it. So 1, 2, 3, 4, 5, 6 times 1, negative 1, 2. So this is really what you're doing. You're just taking a linear combination. I mean, basically all we're doing is we're taking a linear combination of the columns of A. So this is just a linear combination of the columns of A. That's important. And the coefficients that you use in front of the columns are just the entries of your vector. That's important. But that's not how I actually do this. So linear combination of the columns of A, you take 1 times the first column plus minus 1 times the second column plus 2 times the third column. If this is starting to look a lot like the previous section, good. So when I'm actually doing this, I need both my index fingers. 2 index fingers. I go, my left index finger moves across, and my right index finger moves down. So beep, 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 beep. So I know I'm going to get a vector with 2 entries. My first entry is going to be 1 times 1 plus 2 times minus 1 plus 3 times 2. And my second entry is going to be 4 times 1 plus 5 times minus 1 plus 6 times 2. In other words, if I do the arithmetic, I get 5, 11. But it saves me a bunch of writing. So first entry, go across the first row, down this. Second entry, go across the second row, down the same thing. Is that okay? It saves you a bunch of writing, but this is what you're actually doing. You're taking a linear combination of the columns. You're taking a linear combination of the column vectors. This is what we call A1, and this is what we called A2, and this is what we called A3. So what we've done here is we've just taken a linear combination of A1 and A2 and A3, and these are the coefficients we've used. But when I'm actually writing it out to save myself a bunch of writing, this is how I do it. Okay, excellent. So let me give you another definition. Given an M, too many bumps, M by N matrix A, vector x in R. So remember, this vector that we put right here has to have the same number of entries that we had columns over here. This is the number of columns, so this is an Rn. And a vector b in R. This time, this vector is going to be in Rm, which is why I'm writing it separately. So this vector has the same number of entries that M had rows. So I have one vector x that has the same number of entries that A has columns, and I have another vector b which has the same number of entries that A has rows.
Does the matrix A need to be and have the vector symbol above it?
Say it again.
In the first given an m by n matrix A, does the A have to have their symbol above it?
Oh, sorry. No. You're right. I wrote this wrong. It should be capital A with no symbol above it. It's not a vector. It's a matrix. Yes, you're absolutely right. I messed that up. Then AX equals B is called a matrix equation. And solving a matrix equation means finding an x which makes the left side equal to the right side. So for example, say A is equal to 1, 2, 3, 4, 5, 6. And let's say B, oh, just for laughs, is equal to 511. Then here's a matrix equation. 1, 2, 3, 4, 5, 6 times x1, x2, x3 is equal to 511. This is a matrix equation. I could go ahead and write this as a vector equation. I could have written this as x1 times the first column, 1, 4, plus x2 times the second column, which is 2, 5, plus x3 times the third column, which is 3, 6, equals 511. So here's a vector equation. Which is exactly equivalent. I could go ahead and write this as a system of linear equations. I could have written x1 plus 2x2 plus 3x3 equals 5, and 4x1 plus 5x2 plus 6x3 equals 11. I could go ahead and write this as an augmented matrix. Save the most writing. Where are we? 1, 2, 3, 4, 5, 6, vertical bar, 5, 11. They're all the same. They're all equivalent anyway. Is everybody okay with that? By the way, give me one solution to this or that or that or that. They're all the same. They all have the same solution. Based on your notes, give me one solution, one value of x1, x2, and x3 that'll work.
1 minus 1 and 2.
Yeah, so x1, x2, x3 equals 1 minus 1, 2. Just judging by your notes, because we already saw that if we plug that in to this, we get 511. This is a solution. Is it the only solution? Is that the only solution? You don't have to actually solve it. Just look at this. Look at the size.
I want to say no, because there would be a free variable.
Exactly. There can't be more than 2 pivot positions here. And we have 3 variables, so you have at least 1 free variable. So the answer is no. We know without solving anything. I mean, you could go ahead and solve it, but before you even solve it, you could just look at the size and say no, because we'll have at least 1 free variable. Right? You can't have more than 2 pivot positions because we have 2 rows. There are 3 variables. At least one of them's got to be a free variable. There's got to be more than just one solution. Got to be infinitely many solutions. How do you feel about this? Is this good? Awesome. So you'll be happy to know that we're just about done coming up with equivalent forms of the same thing. We have 4 of them. I mean, I suppose we could make up another one, the Hoogie Flukes, whatever version of this, but this is basically it. And this is the one that's most convenient to do computations in. We convert generally to this when we're doing computations. This makes most sense when we're thinking about topics that I haven't talked about yet, called linear independence and span. This makes most sense in some ways, and this is certainly fundamental. That's the first way you ever saw, systems of linear equations. And so each one of these things has an advantage. But we're all looking at the same thing over and over again. If you have no questions, I see I'm out of time. I will let you go and have a good weekend, and I will see you on Monday.